This video will demonstrate how to measure and analyze the reverberation time of an office using Dirac. We want to know the reverberation time in each octave frequency band ranging from 63 Hz through 8 kHz. The hardware consists of an omnidirectional microphone and an omnidirectional sound source, each connected to a 2755 power amplifier that now serves as a power USB audio interface to the PC. The 2755 gain after power on is -30 dB, which is a safe value to start with. We open the measurement window and starting with the source settings, we have to choose a stimulus from a pull-down menu. The low-pass behavior of walls and other kinds of partitions contributes to the dominance of low-frequency background noise in rooms, making pink spectrum stimuli the typically preferred choice for room acoustic measurements. Candidates are therefore pink MLS and E-sweep. Other stimuli have a wide spectrum or are specials. Each of the candidates is available in a wideband and a band-limited version. Because the measurement has to include 63 Hz, which is missing in the band-limited versions, a full spectrum stimulus is chosen. In general, even if band-limited stimulus would do, as a rule of thumb, if there is no reason to use a band-limited stimulus, use the wideband version, as the wideband stimulus bears more information, which may be useful for future analysis. In case of the pink MLS stimulus, the reason for band limitation would be that you need as much of the available power from your amplifier as possible and don't want to waste any power on sound outside the frequency band of interest. In case of the E-sweep stimulus, the reason for band limitation would be that your loudspeaker source has difficulties handling very low or high frequencies at high power levels. Neither of the reasons play a role in this silent office, requiring only little stimulus power, so a wideband stimulus will be chosen. Compared to MLS, the E-sweep is less sensitive to changes during measuring and enables the elimination of distortion effects, but it is more intrusive. Because intrusiveness is neither an issue here, E-sweep is chosen. We are not measuring a speech intelligibility related parameter requiring the absolute background noise level, so we leave the intermittent checkbox unchecked. In this office, the expected reverberation time is well below 2 seconds, so we choose a stimulus length of 2.7 seconds, as this value will exceed the reverberation time in each relevant frequency band, while the measurement will not take unnecessarily much time. On the Device tab, it is verified that the proper sound device setup is selected. Now, with the gain slider in first instance at a low value, say around -30 dB, we click the Test button. If a sweep is heard, the gain slider is moved up until either it reaches 0 dB, or the VU meter indicates an overload, or distortion of the sound is hearable. Then the Stop button is clicked. For the derivation of the reverberation time, the received signal will first be converted to an impulse response and not used as is, so the impulse response or IR button is clicked. We only have one microphone, so the receiver hardware configuration is set accordingly, being a single omnidirectional microphone. The sound level for this hardware setup is calibrated, as can be seen here in the status bar, although this is not mandatory for reverberation time measurements. On the Channels tab, it is verified that the output and channel 1 are checked. Input 2 is not used and therefore unchecked. On the Project tab, Autosave is unchecked. Now we will start the measurement and keep quiet until the signal graph occurs. This is the resulting acoustic impulse response. The tail shows negligible noise, which indicates a successful measurement. Now, to get a quick impression of the reverberation time, we click the Project Parameters button, and in the Properties dialog box, Reverberation, T20, full octaves from 63 through 8 kHz, and a vertical range from 0 to 2 seconds. Then OK. The resulting curve looks pretty normal for a novice. Now let's discuss some details. When we click the Energy Time Curve or ETC button, the full spectrum energy level in dB is plotted versus time. The decay resembles that of an interrupted noise response, but would deviate more as the decay deviates more from a pure exponential one, such as with coupled rooms that show a kink in the decay. The reverberation time, which is the time to decay by 60 dB, is by definition based on an average over multiple interrupted noise decays. It is shown by Schröder that backward integrating the impulse response energy results in a function that is equivalent to the average over infinite interrupted noise responses. This function is the decay curve and can be viewed by clicking the corresponding button. The slope of the decay curve is an accurate measure for the reverberation time. But because the decay range is normally smaller than 60 dB, an estimation of the reverberation time is made by extrapolating the part above the noise floor. This estimation of the reverberation time is called T30 if it is derived from -5 through -35 dB, and called T20 if it is extracted from -5 through -25 dB. The selection shown here is made by dragging the cursor. Detailed information of a selection or the complete capture can be viewed by clicking menu item View and then Info. For instance, this selection from -5 to -25 dB has a decay time corresponding to a 60 dB decay of 0.3 seconds, which is therefore approximately T20 over the full spectrum. We can examine frequency bands by clicking the Filter button and choosing a band, which is then shown here. When we choose the ETC curve again, turn off Auto Scale and step through the frequency bands using either of the filter stepping buttons, we see the decay range change, partly due to different impulse response levels in each band and partly due to different background noise levels. Because of the importance of the decay range to the reliability of the reverberation time and of most other parameters derived from the impulse response, an algorithmically calculated estimator of the impulse response decay range was defined, being the impulse response to noise ratio, INR, which is a good impulse response qualifier. In fact, the INR qualifies an impulse response in the same way as the signal to noise ratio or SNR qualifies a signal. Both the INR and the SNR can be improved by increasing the signal level or reducing the background noise level. The difference between these qualifiers is, however, that only the INR can also be improved by increasing the measuring time. Now we click the Project Parameters button, and in the Properties dialog box, choose Level, INR, full octaves from 63 through 8 kHz, and a vertical range from 0 to 100 dB, and then OK. According to the ISO 3382 standard, a reliable T20 requires an INR of 35 dB and a reliable T30 an INR of 45 dB. Therefore, as easily visible in the table view, in octave bands, T20 values would be reliable from 63 Hz and T30 values from 125 Hz. In third octave bands, these frequency lower range limits would be 100 Hz for T20 and 160 Hz for T30. Note that the most recent parameters are available in the top right pull-down list, so we now can easily switch back to the T20 graph. It is also possible to open multiple instances of the project parameters window, where in a second instance of the window, for example the INR, is selected. After which both windows are placed side by side. This brings us